Welcome back for the third video of 6.1. I understand I'm not actually starting here in 6.1.2. We're doing the example right beforehand, but that's because this one is like a prelude to the next piece. It's example 5. We're graphing a general solution, and our instructions are graph the family of functions that solve the differential equation dy dx equals cosine x. This is an interesting phrase, family of functions. I don't think we've said that yet, so we definitely want to find out what is meant there. This seems like an easy differential equation, though. Dy dx equals cosine x, so we know the solution to that's going to begin with y. Let's see, what function has a solution of cosine x? That's sine of x, and we know that for a general solution, we want to make sure we have plus c. So now we're asked to graph the family of functions, and I want to start to think about this general solution as you would graph it in your calculator or Desmos or by hand. It's going to be the sine graph plus a c. So if you maybe added 1, it would be the sine curve. If it was shifted up one space. If you subtracted 2, it would be the sine curve, maybe shifted down a couple of spaces. So let's think about this. We know the sine curve as it sits is a curve that kind of goes, the wave form there. It goes forever and ever in both directions because it's always continuous across the real numbers, and it looks like this. Let's see, what if we had c as 1? It would shift up one space to here, and so that would look like that, and maybe we'd come over here, and so there we go. What if it was c is -1? So we'd shift it down a space. So we would start to look like this, and you can kind of begin to see now what was meant by a family of functions. This is a set of, an infinite number of functions that all differ by some constant. We know that adding or subtracting a constant to the end of a function is just a vertical shift. This family of functions all looks the same. They're kind of parallel, I suppose. And they just have a vertical shift between them. You can actually do this in your graphing calculator pretty quickly with lists. I wanted to show you how. So you start with some brackets, so second, and then that, actually it's a brace, excuse me, above the parenthesis, and you can type in, we can go like -2, comma, -1, comma, 0, comma, 1, comma, 2, and then end the brace. And then what you do is store that as a list. You hit the store button, and then the lists are L1, L2, L3. So hit second 1 for L1, store that, hit enter. Now it's in there. Oh no, I meant 1, 2. I hit minus instead of a comma. I got to try that again. Let's see, that -2, comma, -1, comma, 0, comma, 1, comma, 2. That's better. Second brace, and then store that as L1. Enter. Okay, there we go. There's 5 different numbers. And if you go to Y1, you can graph sine of x plus just L1. And what it's going to do is give us that whole family. Watch this. 1, 2, 3, 4, 5. Hey, there they are. And we actually did a pretty good job of graphing those ourselves. There's the family of curves. So back to here. And here's a question from the textbook that I think we're going to leave to class time. And I just want to move through to get, there's the answer that we had. This list was a little bit bigger, but notice it's a family of a bunch of parallel curves. And like we discussed, that's no surprise. It's sine of x plus c, and plus c is just a vertical translation of the sine curve. But what might not be so obvious is we could have predicted what this looks like without solving the differential equation. Like, we could have been sitting there with dy dx equals cosine of x, and we could have known just with this, without going through the sine of x plus c, that this would be the field of the family of curves we would find out. There's an exploration that takes us through that process step by step, but I just want to kind of start with that as our motivating thought and move right into slope fields. No new definitions or rules or theorems here. Oops, we actually do have a definition. It's slope field. I guess I should have written that over here. Slope field is coming up. All right. So we didn't do the exploration. We might do that in class, but for right now, just begin with that thought of the family of curves. Let's say we wanted to produce that figure without actually solving it. That's where we are now. Okay, we're right here. And since that differential equation gives us the slope at any point xy, that's what a differential equation does. It tells you the derivative value, which is the slope. We can use that information to draw a very small piece of the linearization at that point, which, thanks to local linearity, is going to approximate the solution curve that passes through that given point. And if you do that process over and over, you end up with what's called a slope field. Here's an example of that. Construct a slope field for the differential equation dy dx equals cosine x. So let's give that a shot. And we know what the solution looks like. There's actually a slide after this that's going to show the step-by-step of how to do this. So let's just begin this way. I'm going to do just the y-axis. So here's a few points along the y-axis, 0, 0, 0, and let's see, this would be 0, 1, and 0, 2, and 0, -1, and 0, -2. So each one of these lattice points, even all the way across over here and here, all give us an x and a y value. We can use that x and y value to evaluate dy dx at each of those places. Let me show you what I mean. Let's start with the origin. Let's evaluate dy dx at the origin. So what we do is plug the x and y value into the differential equation. In this case, there's no y value involved. It's just cosine x. So all we need is the first value. That's cosine of 0. And then that's cosine of 0. Oh, we know that's 1. So think about a slope of 1. We know that that's a line that would look something like this, slope of 1. What we're going to do is go back over to that point 0, 0, and just make a little line segment that has a slope of 1. And we could move up to 0, 1 to try to evaluate dy dx at 0, 1. And again, since there's no y value involved in this differential equation's right side, all we need is the x value. And we're at cosine of 0 again, so that's 1. And once more, same slope. So we'd go to here, and you can probably surmise that along the entire y-axis, we're going to have this sort of shape. So moving on to the next slide, you can see this process start to follow through. Part A, that's what we did, all of the slope 1s across. Then let's go to part B. We've now taken, let's see, this is a pi over 2 here. That makes this pi. So all of these points begin with pi. And if you think about evaluating cosine of pi is -1. Oh, okay. So yeah, that makes sense then that all of these slope markers are kind of like line segments with a slope of -1. Over here, this is negative pi, which actually is on a unit circle, the same location as pi. So the cosine is same, and that means all of these are going to be -1s as well. All right, we're starting to take shape here a little bit more. Let's move over to C, and now we've gone into the pi over 2s and the 3 pi over 2s. Think about cosine at pi over 2. Well, that's 0. And same at 3 pi over 2, yeah, that's also 0. So if we think about slope of 0, that's a horizontal line. So we take a tiny little horizontal segment and put it in place at all of those lattice points. And all of a sudden, we end up with this shape like D. Now, follow along with these tiny little line segment slopes. What happens if you just follow the path? How about that? These are all of the tangent slopes at all of these points of the differential equation cosine x, but watch as you follow these waves along, it produces a family of sine curves. Why is that significant? Because sine curves are the solutions to that differential equation cosine x. Let's move along. And here's one from our textbook for us to create ourselves. It's a pretty easy differential equation. dy dx equals x. So all we need is the x value of every one of these points. So let's go through. Let's begin with the origin. You don't have to start there, but I usually like to because the math is easy. The x value is 0. You plug it in, you get 0. So I'm thinking about a line segment with a slope of 0. It's there. Move up, there's 0, 1. It's still going to be, oh, right. There. Okay. So, and then up 0, 2. So we just need the x value. It's 0 again. So this whole segment's going to be 0. And then let's go to the right. I like to move from the origin over to the right because it's positive numbers. And again, that just makes the math easier. So all of these points up and down are going to have an x value of 1. And you plug that into the function there, you get 1 out. And so I'm thinking a line segment with a slope of 1, and those are all going to look the same as well. And then to the left, -1, same idea. Plug that in, you get -1. All these x values are all we care about. They're all -1. There are my line segments of -1. So this is the beginning of the slope field for the differential equation dy dx equals x. And what's significant about this is if we just follow the wave, follow all of these little line segments that represent slopes, we should end up with something like this, or like this, or like that. And those all look like parabolas, don't they? Well, think about the solution. The solution would be 1/2 x squared plus c. What's 1/2 x squared? That's a parabola. Plus c, it moves it up and down. There's your slope field of all of the solutions there. And inside of that slope field is the family of functions that represent the answer. I think that's so cool. And so here's the graph that we made in that example with all of those sine curves overlaid on top. There's a program that I'll get out to you next week for your TI calculators that kind of do slope fields. TI-84s don't have a slope field function built into them, so we have to run a program to do it. Whereas if you have a TI-89, that one's got slope fields built in. And I'll show you how this works. That was from our video earlier. Let's clear this all out. Go to y equals, and what's going to happen is you're going to type your differential equation here. So we might type just x. That was the last one that we did. Hit enter, get out of there. Hit programs. I've got a couple different slope field programs going on, but the simplest one is this one that just takes out the vowels. It's Slopefuld or slope field. Hit enter there, run it, and there it is. So this is an approximation of the slope field, and that should look fairly similar to what we did. The one drawback of this one is I can't really make all of those little line segments happen at the lattice point. So we don't get to see that flat 0, 0 along the piece. That's why I have that other program. It's a little more full-featured, but this one is just easier to run. And you can tell that if you follow that wave, you're going to end up with some parabolas there. Back to the notes. Here's another example. Use a calculator to construct a slope field for this differential equation and sketch a graph of the particular solution that passes through the point 2, 0. So this one's x plus y. Let's try that calculator program again. So I'm going to go back to my y equals screen. X plus, now to get to y, we're going to have to go alpha 1. Now, don't try graphing this. Don't hit the graph button. Your calculator's not going to like it. You can't put y's into a function form, but you can do this, hit enter, just get out of there, and now your program can use it. So we're going to go to slope field program once more, hit enter, and we should, oh, interesting. Okay, so we've got all of that, and that move. This is not a parabola. I'm really not sure. It's almost like there's a diagonal type of asymptote almost, and then if you follow these waves, you move really, really vertically quickly as you move across to the x-axis. So if we go back to our notes, I think we even might see that. Do we? Oh, I thought there was going to be an answer to that one there. I couldn't recall from the last time. So maybe what we can do then is back here, and can I take a picture of that? Yeah, let's do that. And let's see, picture that. Let's copy it. Wonderful. I don't care, I can't cancel. Let's go back over here. Let's paste it. Then, awesome. Let's go over here. Now, we want to sketch the particular solution that passes through the point 2 comma 0. So what we want to do is find 2 comma 0. That's right there. And then from 2 comma 0, just follow the flow. So it looks like we're just kind of following the flow this way. Follow the flow of all of those little marks. And I think our solution, I'll try to smooth that out a little bit, is going to look something like that. Just follow the little line segments. All right, so here's an example. We just need to use, a little bit of mental math. Okay, slope analysis, which is basically just mental math to match each of the following differential equations with one of the slope fields A through D. Okay, let's go to number 1. dy dx is x minus y. So let's start maybe at an origin. If we were going to go 0, 0, we would get 0. We'd be flat there. Notice in part A, all of the line segments around the y-axis are zeros. So if we plugged in a 0, 1, we still get 0. 0, 2, we still get 0. That doesn't apply here. That's interesting. That's really making me think this x, y, because if the points along the y-axis are all going to be 0 comma y value, multiplying x by y would just get 0 every time. I'm thinking this is an answer right now. Oh, you know what? D could be as well. So let's hold off on saying that. We're still kind of trying to focus in on 1. So what would happen if we went up to like the point 1, 1? Wouldn't we get 0? Or 2, 2, wouldn't we get 0? Or 3, 3, wouldn't we get 0? So that means along the diagonal that has all of the 1, 1, 2, 2, 3, 3, 4, 4s, I should expect a slope of 0 that whole time. Do we see that anywhere? Along the diagonals, a slope of 0. At the moment, I am not. Along the diagonals, a 0. I see along the diagonals a 1. That's interesting. Diagonals is 0. Not so much right now. Interesting. Let's see then. Let's try a few more. What would happen if we went along the x-axis and went to like a 1, 0, 2, 0, 3, 0, 4, 0? We're subtracting 1. So as we move along the x-axis, we would expect the slope to get bigger and bigger and bigger. And let's see. That's making me think here, right? So here's kind of a tighter slope, getting a little steeper, little steeper, little steeper, little steeper. And yeah, this is going to be the answer. This one's going to be B. I can see what's going on here. These graphing calculator setups are not one-to-one. So I was looking for X, Y's kind of along a perfect little diagonal, but that's not actually a perfect little diagonal. And you can tell when I wanted that 0, 0, it's like right here. There's your 0, 0 that we were looking for a while ago. And that was, I guess, on me for not recognizing that this was a one-to-one scale. So there's B. So we're done on that one. We know that number 2 is either A or D. Let's narrow that down a little bit. If we get a big X value and a big Y value, we would get an even bigger product. So that would be a really, really steep slope. And you can tell over here, look how steep those are. They're almost vertical. So this one's going to be D. So we've got B done. We've got D done. And now we've got an X over Y and a Y over X. So let's see. If we've got Y over X, we know that positive over positive and negative over negative are going to be positive slopes. Both A and C work there. What's going to be, I think, the determining factor is if your y's are 0, then you're going to be undefined. There's not going to be a slope. We'll check out part C. Here's where your x's are 0 and you're undefined. Okay, interesting. But then look at part A. Here's where all of your y's are 0 and there is no tick mark along there. In fact, it would be straight up and down, which is an undefined slope. It's a vertical line. It's undefined. So that makes 3A, and that makes number 4C. So B, D, A, C. Here's an exercise from your book that's probably something good for us to do in class, and that means we're out of the videos here. So enjoy your weekend, and I will talk to you in class next week.